Hi, folks. We've been talking about how do you detect black holes. Well, aside from the other methods we've mentioned, gamma ray bursts and hot accretion disks and things like that, one of the other ways that you can detect a black hole is via gravitational waves. Now, gravitational waves were first predicted by Albert Einstein not quite a century ago. And gravitational waves are a disturbance in the fabric of space-time caused by a large change in the force of gravity. Now, you're familiar with gravity and you're familiar with waves. You have dropped a rock into a pool of water and you get a rippling wave pattern that kind of circulates and goes outward out from that epicenter of where that dropped rock actually hit the ground or hit the water. It was hypothesized that if you had a huge change in the force of gravity, if space is not nothing, space is something, if it is this flexible, movable fabric of space-time, if there is a huge gravitational event, it could send ripples through this fabric of space-time. And if there are ripples, we could be able to, or should be able to, detect those ripples. Now, what is a large enough gravitational event to create something that we can detect? Well, it's got to be a big one, and a big, big, big gravitational event. So something like the merging of black holes. Black holes merge in order to create supermassive black holes, and we know supermassive black holes exist in the centers of galaxies. They are millions and billions of solar mass black holes. And so the only way we know that supermassive black holes can exist is by lots of solar mass black holes combining. So we know that black holes constantly have to be merging. Well, if you take two black holes, which are huge gravitational objects, and you slam them together, that has got to create some pretty extreme ripples in the fabric of space-time. Other possibilities are neutron stars colliding with each other. These are huge gravitational objects, or a neutron star colliding with a black hole. Any of these could be a big gravitational event. The LIGO Observatory was built less than 10-15 years ago. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And with a name like that, hence people use the shorthand LIGO. There are actually two in the United States. There is one in Louisiana in the southeastern part of the country, and one in Washington State in the southwestern part of the country. So Louisiana is down, forgive me, all your geographers. So Washington State is up here. Louisiana is down in here, and these two experiments are purposely separated by a couple thousand miles, and that is done on purpose. This experiment was first put into production or put online a little before 2015, and almost immediately the very first gravitational waves were detected. So how does the LIGO experiment work? Well, it works like this. There are two long tunnels. Now, each one of these tunnels is 4 kilometers long, very, very straight, probably the straightest tunnels known to man, 4 kilometers or about 2.5 miles long. And there is a laser beam that is fired down each one. This is a very fancy laser, much more specific than the one you use to entertain your cat. And these laser beams are perfectly synchronized. So a laser beam is sent down one tunnel, it hits a very precise mirror and comes back. A laser beam is sent down the other tunnel, hits a very precise mirror and comes back. If everything is normal, those two light waves, because light is a wave, when they come back, the two light waves will interfere with each other in a very precise way, and all will be right with the world. If a large gravitational event like two black holes merging occurs, here's what's going to happen. the light waves coming from one leg compared to the light waves coming from another leg are going to be a little bit out of sync. So perhaps because of the fact that these gravitational waves are going to cause space itself to be stretched, perhaps in one direction, and going to be shrunk a little bit in the other direction. Two light waves that when they met looked like this, one on top of each other. When this whole 4 kilometers of space is stretched and this one is shrunk a little, instead of the light waves perfectly aligning, they actually interfere. That's why the name is interferometer. They interfere with each other, and so you end up with one light wave that looks like this and one that is a little bit off kilter compared to its brother, and you end up with an interference between the two light waves, and they are a little bit out of sync. The reason there are 2 experiments, one in Washington State and one up in Louisiana, is because of the fact that the duplicate experiments help to confirm that they're seeing the same thing. If they both get the same readings and they're both coming from the same direction in space, it's an indication that it's not just a stray vibration that's coming from a truck driving by or outside interference. And astronomers and physicists who are working with this equipment, they have to use their technology, use their computer skills to remove all of the background trucks driving by and people walking down the road, because all of those are causing vibrations, and they have to eliminate that and hone in on just the waves that are coming from space. Kind of a cute story about the LIGO experiment. When it first went online in 2015, what I've read is that the experimenters just set it up. They were doing some test runs, and all of a sudden they got a reading, and they were like, was that a gravity wave from outer space, or was that just a glitch in the system? And the 2 Louisiana and the Washington people kept talking to each other and went, whoop, we got the same reading and we're a long way away. So it might be the real deal. Almost immediately, the experiment started producing good results, and people in science were very, very excited. Now, immediately after the wave is detected, the word goes out to optical telescopes and radio telescopes. So astronomers around the world are going to point their radio telescopes and their optical telescopes in that direction to see what they can actually see. Can they see black holes? Can they see gamma ray bursts? What else can they see in that direction? This is a radio telescope image. And can they confirm with other methods of observation what they're actually seeing? So in 2017, the detection of gravity waves, this is 2 years after the experiment went online, gravity waves were first detected. The Nobel Prize in Physics was given to these gentlemen, Rip Thorne, Barry Barish, and Rainier Weiss from MIT. These gentlemen for their original proposing the idea of conducting this experiment. This is a big, big, big deal in the history of science. So why is it such a big deal? Well, it's a big deal for a whole bunch of things. One, it proves that gravity is a force that travels. It's not just a thing that is, it is a force that travels. Light takes time to travel. Gravity is a force that travels, and it travels over a distance just like light. That's pretty cool. It's proof that black holes merge. These things come together and merge. Our hypotheses have always said that, you take little black holes, you smear them together to get bigger black holes. Well, we can detect those mergings now, and that's a pretty cool thing. We're finding that every time a black hole, a neutron star, or a combination thereof are merging, we get different results. Not every gravity wave is the same. They're coming from different parts of space. They're coming from different spaces and regions, and the optical telescopes are looking in those directions immediately afterwards. We're getting a whole bunch of new information about these really, really unique and bizarre elements in astronomy. And so it is a brand new age in astronomy. So much so that this is a whole new tool for astronomy and for science. Up to now, we have been limited to the electromagnetic spectrum, visible light, radio waves, things like this. This is a new tool. We have never looked with gravity. And that is so exciting. It's a very exciting time to be alive in science, to actually use gravitational waves as a way of observing our universe. And one of the biggest things is it's proof we're on the right track. As human beings, we're trying to explain what we see in space, what we see of our universe, and what we think we're seeing. Our experiments are saying, hey, yeah, you're seeing black holes merging, you're seeing neutron stars and black holes, and the math is matching what you think you're seeing, and you're learning some cool new stuff along the way. So it is a big, big, big deal, gravitational waves. There's a lot more exciting things you're going to see in the next decade about gravitational waves. Many other countries, there are lots more experiments that are being produced. This equipment, many other countries are building LIGO type experiments because the US happened to put their experiments up first, and other countries are catching up. They're going, we want one of those too. All right, that will conclude our discussion of black holes. You have a fabulous week. I've got a couple cool videos explaining this in more detail. I hope you take a few minutes and watch them. Talk to you soon. Bye-bye.